Hey guys, welcome back to our next class. Now we're gonna be talking about malware tricks. So basically, um, you will learn a lot of malware tricks when trying to analyze it, because malware authors, they really wanna make your life harder. So they don't want you to get to the meat, at least not to get that easy. So they will use many techniques to try to avoid being analyzed, right? So there are many techniques here, guys, that are not used anymore, but I really like to keep them because those are for the purpose of explaining you what the authors does. uh, that's the important thing, because we will keep obviously adding more and more, and you will see in the labs many new techniques being used nowadays. But I really like to remember those ones that used to be used in the past. Okay, so we're gonna be talking about anti-debugger tricks. Techniques to know by the malware authors if you are using a debugger. If you are running the malware inside a debugger, they will try to detect it. If it is being used inside a virtual machine, the packers, like what are the packers? We talk about packers a little bit in previous classes, and the idea here is for you to understand more into how the packers are being used for these guys to try to make it harder for you to analyze it. Process injection is more like ways for attackers to hide in memory. This is actually my favorite topic. Process injection is just amazing. It keeps evolving. I'm gonna be talking about some of my favorite techniques, like process hollowing. I remember I found out about it back in 2014, probably, and that's actually pretty amazing. It's still being used today, but actually the way they execute it is just brilliant. So again, it's known techniques, but the idea is for you to understand the theory. Okay, don't worry again about the theory. This is for fundamental, for you guys to be ready for the labs, and we're gonna be practicing a lot. Windows hooking. So what is Windows hooking, and how is being used maliciously by the attackers? Hidden desktops, a pretty nice trick. Also, again, very old, not being used lately, but pretty cool one. And eventually you will learn how to find the new ones in the labs that we're gonna be showing you. Okay, so let's go by anti-debugger tricks first. So as I said, these techniques are for malware authors to see if they are being run inside a debugger. So the basic 101 check is the Windows API is debugger present. So basically they call this function, and this function basically it walks the process environment block. Don't worry about the process environment block. We will see that in detail because we are going to be using it for malicious purposes. But the process environment block is a very important structure that every process running in memory has. It has a process environment block and a thread environment block, and both together allows the process to know where it is located in memory, which is the base address, which are the modules loaded, which are the threads associated, which are the register values, the local physical path in the file system, many information. And one of those fields into this structure is one field called being debugged. Being debugged is going to tell the process if actually it's been running inside a debugger. So the attackers, what they do is they call this Windows API is debugger present, and if it returns non-zero, that means there is a debugger. Okay, can you imagine how you can bypass this check by the malware? Normally you go and check the return value of 0. You change it to 0, so that the malware thinks there is no debugger, right? So you will see some ideas, but this is the basic one. Another one that was also used back in the day, check remote debugger present. It's another Windows API. It's the same idea as the is debugger present, but this can check other processes, not only the current process that you are using. Anti-query information process. This is another Windows API, and this was actually pretty cool one back in the day, because this actually checks the process debug port, which is the number 7 value of the process. And if it returns 0, there is no debugger. And this is something that I really want to point out, guys. If you see this, it's not about these Windows APIs, because these are old ones, but understand the process. You see, like these guys learn this API and realize there is a process debug port, and then they use it to know if there is a debugger running. Like every time you're going to be analyzing malware, you're going to suddenly see APIs that you had never seen before, and then you're going to go and start researching for them, understand what they do, and eventually what happens is like, hey, you know what, this API is checking like if there is a specific field in a virtual environment, or that inside a debugger, and it's when you realize there's a new technique that malware authors are being used. And these guys are always been keeping updated on those new APIs that normally the ones that are not documented, for them to keep adding more and more ways for them to evade being analyzed. Okay, another one, output debug string. This was pretty well known back in the day. You might not know about a version of Windows called Vista. That was, I think, the last version of this API. Is deprecated now, but again, guys, it's just for you guys to see ideas of and real example of how these guys used to do this kind of checks. No, so the output debugging, basically, this API, it used to send a string message to the debugger console. But if there is no debugger console, then it will throw an error. So the malware author says, okay, you know what? If I call this function and there is no debugger, it's going to throw an error, and then I'm going to realize there is no debugger. So let's see how that works in a quick pseudocode. So the malware author says, like, I'm going to put an error value of 1, 2, 3, 4, 5. I'm going to say, this is my last error that I found right now in my program. Okay. Then they call output debug string with this string, test if debugger is present. And let's suppose that there is a debugger running. Okay. So what's going to happen is this API is going to throw that message to the debugger. Everything is fine. There is no error because there is a debugger. Then the guys are going to check, hey, give me the last error that just happened in this program. And it's going to say, you know what? The last error is actually 1, 2, 3, 4, 5. It's the same. What that means is there is no new error that just took place. In other words, there is no error generated by call this output debug string, and therefore, if there is no error, that means this execution worked, and therefore there is a debugger that was able to print out this string. Okay, and then if that's the case, these guys just get into an infinite loop, or just exit the program, or do whatever they want. Now, if there was not a debugger, it would have not been a debugger in the system, then this would have thrown an error like, no, I don't know, error 0005. Then these guys are not the same anymore. There's an error. Then the guy says, great, there is no debugger, and then I run the malware. Okay. Let's see another one, process heap flag. Again, guys, these guys go deep into the operating system to understand. That's what I really get amazed about the threat actors. For example, this one, again, goes to the process environment block structure and search for the location of the first process heap. When a process runs, it has multiple heaps running in memory, gets the first one, the default one, and some fields in the header of the process heap tell the kernel whether the heap was created by a debugger or not. See that, man? See that, guys? It's like amazing, right? And then if these guys get that content, and that is gonna tell you if there is a debugger inside. Pretty clever. Anti-global flag. That's another pretty cool one. Also, back in the day, was used. This was used to be undocumented, and that's used to check the undocumented value of the PEV at offset 68 hexadecimal, which helps the system to decide how to create memory heaps. If the value at this location is 70, the system or malware knows there is a debugger. But again, guys, I want to stress this. Check how these guys understood the PEV structure, understood the 68 offset in the structure, and realize that there are different values when there is a debugger not present. And this is when you are doing the analysis. And to me, this is one of the exciting parts when you are doing analysis of malware. When you said, hey, what is this structure? What is this offset? And eventually you see that the program exits. Boom, you just got a new technique being used by the malware authors. Default debugger in the registry. So normally you can configure the registry to see if there is a debugger, and it's gonna be open automatically when an application error occurs. Okay, so for example here, you have this path in the registry where you can put the AE debug, the debugger you want to use, and you can put, normally set to Dr. Watson. Back in the day, used to be like a default Windows debugging mechanism to throw what was an error in the system, but it can be set to WinDebug, only debug, right? So then it's another way for the malware to know if there is a debug configure to be open by the analyst. You can search in the system. This is normal one, guys. The malware can check in the system if there is any program files that tells you there is a debugger installed, and therefore that means it looks like an analyst machine and not like a normal machine. Keep in mind that the malware authors do those checks because they really want to make sure that they are in a real machine of the victim. If they notice there is a clue that they are in a machine that is from an analyst, they just want to exit, okay? Another one, pretty cool one. They can search for open windows in the system. Those open windows, if you open a notepad, it has a title. So you can use the find window API and check if there is a window with a title that is related to a debugger. Like only debug. Then they said, what? There is a window open and it is part of a debugger. So then I know there is a debugger running in the system. And then the program is going to exit, okay? Int scanning. This was pretty cool back in the day, guys. That throws me a lot of problems, and I want to explain you why. So int scanning. Int 3 in x86, it is a software interrupt used by the debuggers to set breakpoints. Okay, so basically the opcode or the byte is hexadecimal CC. If you put that hexadecimal CC into a program, when the debugger steps into that instruction, it's going to stop. It's like a breakpoint for a debugger. Okay, so what the malware do is going to go and scan the whole memory space and see if there is an unexpected CC value. Unexpected because there might be CC values for other reasons, but if it is a CC value inside their code, they know there is a debugger. Imagine this, guys. this is very important. So let's imagine that the malware has a FE byte value, right? In a specific offset, there is a FE hexadecimal value. When you set the breakpoint, the debugger is gonna override that FE with CC so that it can set a breakpoint and stops in that instruction, okay? So that's what the debugger does. So when the malware runs, it says, hey, wait a minute, let me check if someone puts a breakpoint, meaning a CC value, and then they will find there is a debugger being used, okay? Let's see these instructions. No worries, guys, this is a little bit confusing for you. You will see that you will learn this whole assembly instructions and many more after this whole training. So call plus 5 in assembly means go to the next instruction. And why? Because call has 5 opcodes, meaning 5 bytes. Call has 5 bytes of an instruction. It's an instruction of 5 bytes. If you say call plus 5, that means go 5 bytes after this call. If you go 5 bytes after, you will land right here, right? Because you move 5 bytes after the call, you reach here. When you reach here, you set pop EDI. That means you will store in EDI the value of this address. Why? You remember stack, how the stack works, guys? When in x86, when you do a call, the return address of the next instruction is going to push into the stack, which is an address here. And then when you do pop, you get that address from the stack and store it in EDI. That's beautiful. Do you agree, guys? Okay, so now, in other words, you in EDI has whatever is the address in memory at this moment, at this point. Okay, then it says subtract 5 bytes, means go back to call right here. And then from there, set a counter in ECX of 400, which is, I think, 1000 bytes. Move to EAX the byte CC, remember the interruption, and then start scanning until you find CC in the next 400 hexadecimal bytes. In other words, guys, this whole loop is going to start from this instruction all the way 400 hexadecimal bytes and try to find if there is a CC byte in that section of the program. If there is, it's gonna find a debugger. That's actually a pretty cool way for them. So I was telling you guys that when I was doing analysis, this was actually pretty nice and for them, right? Because what happened is, imagine that you put a breakpoint and eventually it's like, hey, I put a breakpoint here and I click play in my debugger and I never reach it. What happened? This can be one of the reasons. The malware detected you and they just exit, you know. Performing code checksums, that's pretty cool because basically if you change something in the malware, like a interruption, interruption CC, then the checksum is going to change. You know, the integrity, the hashing mechanism is not going to be the same, and they will detect that there is a change in the program. Timing checks, guys. Oh, sorry. Timing checks, guys. So when you are doing a debugging process, you will go step by step, and that means it will not run as fast as if the program is running without a debugger. So what the malware does is, hey, I want to check how long it takes, you know, and if you go slower, I know that you're not getting the next instructions faster, then there is something there, and therefore you're going really slow. That means you're going step by step manually, and I know there is a debugger. Okay, so the malware checks the before and after specific instructions, check the time it takes, the elapsed time, and realize there is a debugger. Okay, some of the instructions back in the day was RDTSC instruction, which returns the count of ticks since the last system reboot, and basically that was the way for the malware to check the time it takes from one instruction and the second instruction, take the difference and see if there is a elapsed time enough to say it's a slow one and there is a debugger. Okay, query performance and get tick count, same thing. They kind of try to understand how long it's taking, and therefore check if it is a debugger. Query performance acquires high resolution to measure time intervals, but same idea. Then another check pretty cool is TLS callbacks. TLS stands for thread local storage. It's for threading management, but it's actually a second entry point in a program. So, in other words, if you have a TLS callback, it's gonna be executed whatever is that in that function before the first instruction or what is called the entry point of a program. Okay, so in other words, for example, here you have your start program at 40.1308 address, but if you have a TLS callback, then that one is going to be executed before the start. And what happened here is that when you put your breakpoint, in the start, you start your debugger, your machine is already infected, and you're just like, hey, what happened here? What's going on? So you realize there is a TLS callback, and then the malware guys already infect your system, or they took whatever decisions they want. But it's very important to see TLS callbacks because sometimes it's when in that function is where they decrypt the malware, they obfuscate code before hitting the entry point. Exceptions, pretty cool one, guys. Exceptions is another pretty nice trick. So the malware will set up an exception handler, and then they will trigger an error. What is an exception handler? So exception handler is a routine that is gonna be called when there is a specific error, and it's gonna be handled by an exception handler. Okay, so the malware is gonna create an exception handler and trigger an error. Okay, so check this. If there is no debugger, so the flow is gonna jump right straight into the exception handler created by the authors. But if it is a debugger, the debugger is gonna cut or intercept that exception handler. Okay, so what that means is if I am running inside a debugger, then I will never reach the exception handler. And check this, the exception handler created by the malware authors has the malicious code waiting for them to be executed. But since it was intercepted by the debugger, then it never hits the malicious function, and therefore it never executes the malicious code. Pretty cool trick also. Malware inserting interrupts. This one, it is like you remember the 0cc, right? When we check the malware authors check if there is a cc interruption because they want to know if the debugger insert that breakpoint. You remember that, right? But here is different. So here the malware is gonna insert this cc opcode, and therefore it's gonna cause the debugger to trigger it. Okay, so So then they are basically attacking the debugger and stopping the execution of the malware, if there is a debugger. Some debuggers tracks their own software interrupts, so they know like, hey, I didn't put that interrupt, I didn't put that breakpoint, so they don't fall into this trick.